Welcome. This is the first of 5 or 6 review videos on topics that will relate and prepare you for Calculus 1. Most of these topics are things you should have seen before. Some things might be at a little bit higher level or be in the boundary of what you learned before, but mostly what you'll see is stuff you've seen before. This lesson will remind you of some very basic mathematical principles and facts that you've learned over the years of taking mathematics classes. These very basic ideas are presented at a collegiate level to reflect the precise and formal nature of math, to prepare you for this course and for other courses in mathematics and the mathematical sciences that you take in the future. This course, Calculus 1, is about understanding properties of real-valued functions of a real variable, so it's crucial that we appreciate and understand properties of the real numbers and other essential number systems like the integers and the rationals. This lesson will review the following concepts: the way we use symbols in mathematics to represent quantities and processes, what a real number is and some properties of real numbers, how we work with numbers in decimal form, the natural, whole, integer, and rational number systems, prime and composite numbers, and the law of exponents. Because mathematics is a discipline founded on rigorous proof of mathematical statements, we conclude this review with a mathematical statement called a theorem and its proof. I've called these ideas basic, but they're basic in the sense of being essential. They're being foundational. Some of these are very sophisticated ideas. They're not meant to be simple, or not, I don't mean for you to think of them as simple. Think of them as essential. In this course, we're going to study real-valued functions of a single real variable. We write them often as y equals f of x, though the symbols may differ. This is a typical symbolic representation of such a function. X and y symbolize real numbers. X is the function's input, y is the function's output, and f symbolizes the function itself. Here, x and y symbolize variables. We also use letters and other symbols to represent constants and parameters. Another example is that of a One example of how we use notation and symbols is when we want to write down the equation of a line. Here's the slope-intercept form of a line given in its general form as y equals mx plus b. Here, x is the function's input, y is the function's output, m is the slope of the line, and b is the y-intercept of the line. Here, m and b symbolize constants or parameters. Specific values for both give a specific line. Another example is the exponential function. You should be familiar with these. They're often written as y equals a times b to the x power. Here, x is the function's input, y is the function's output, a is the y-intercept of the function, and b is the base of the exponential function. Here, a and b symbolize constants or parameters. Specific values for both give a specific curve, a specific exponential function. Often when we are applying mathematics to understand specific phenomena, these constants take on values and give us specific functions, like y equals 3x minus 2, or y equals 7 times e to the x. But sometimes in this course, we'll work with functions in a more general and abstract formulation where the parameters don't take on values and remain symbolic. Real numbers. A number that can be expressed as a finite or infinite decimal is called a real number. A number that can be expressed as a finite or infinite decimal is called a real number. We can think of the set of real numbers forming a number line, which we sometimes call the real line. If x and y are two different real numbers, then one is larger than the other, which we can write using an inequality, say x less than y. On the real number line, x is to the left of y, and here's how we might diagram that out. Because there is no biggest real number, positive or negative, the real line goes on forever in both directions, and we denote that with the arrows on the end of the line. This now is tempting us to talk about infinity, which we denote by the sideways 8, but we'll delay that conversation for a little while. Real numbers have two binary operations, addition and multiplication, that allow us to combine real numbers to get new real numbers. Properties of these operations are very important because functions and other objects of study in this course inherit these properties. So here's a fact. If x and y are real numbers, then so are x plus y and x times y. This means, and this is some technical jargon, this means that reals are closed under addition and multiplication. Take two real numbers, add them together, you get another real number. Take two real numbers, multiply them, you get another real number. Not all number systems have this property. One thing to note is that addition is kind of a gateway to multiplication. X plus x is what we think of as 2x. And multiplication is a gateway to exponentiation. X times x is what we think of as x squared. So just keep that in mind, because those are other operations that we want to study, namely exponentiation. There are sets of properties that tell us how addition and multiplication work, and, in one case, how they work together. I will list them now. Commutativity of multiplication. X times y is y times x. The product of two numbers doesn't depend upon what order you multiply the two numbers in. Associativity of multiplication. If you have three numbers, it doesn't matter what order you multiply them in, you'll always get the same number. Commutativity of addition. If you have two numbers and add them, it doesn't matter what order you add them in, you'll always get the same number. Associativity of addition. If you have three numbers and you add them, it doesn't matter what number or what order you add them in, you'll always get the same number. And distributivity tells us how multiplication and addition work together. Here, this is often described as multiplying across addition. Using addition, multiplication, and exponentiation together are governed by order of operation rules. To evaluate or expand complicated expressions that involve more than one act of addition, subtraction, multiplication, division, or exponentiation, we follow order of operation rules. A popular mnemonic in the U.S. for the order of operations is PEMDAS, where P stands for parentheses, the first thing you address. E stands for exponents, which would be the next thing you address. M and D are multiplication and division, respectively, which is the next thing you would address. And A and S stand for addition and subtraction, which is the last thing you would address in an expression. Here's an example of how we use those. Take the expression 3 times the quantity 5 minus 2 raised to the third power plus 15. The order of operations tells us how to evaluate this. Specifically, we do it in the following order. First, P, we look for the parentheses, the groups. Here we see we've got the grouping 5 minus 2. So we evaluate that first. 5 minus 2 is 3. The next letter in PEMDAS is E. Look for the exponents. We've got one exponentiated expression, the 3 to the third power. 3 to the third power is 27, so we evaluate that. Next, we look for the M and the D, the multiplication and division. Here we've got one expression with multiplication, 3 times 27. We evaluate that next and get 81. Finally, we're left with one more operation, the operation of addition, 81 plus 15, that's 96, and we're done. Decimal representations of numbers. A real number is a number that has a decimal representation. The root deci means from 10, and decimals are often called base 10 representations of a number. Here I've got a decimal number, 381.0259. Let me explain to you what the different numerals represent. So first, one of the symbols here is the dot. That's the decimal point. To the left of the decimal point, we'll look at the numeral 1. That's a digit in the ones place. The numeral 8, that's a digit in the tens place. The numeral 3, that's a digit that's in the hundreds place. To the right of the decimal point, we have the numeral 0, that's in the tenths place. We have the numeral 2, that's in the hundredths place. We have the numeral 5, that's in the thousandths place. And we have the numeral 9, that's in the 10,000ths place. So here's an explicit way that the tens come in. Looking back at the 1, the ones place, 1 is the same thing as 10 to the 0. 10 is the same thing as 10 to the 1. So that's the numeral 8. Looking at the hundreds place, 100 is the same as 10 to the 2. You can imagine if you have more and more numerals going to the left, how their places become 10 to the third, 10 to the fourth, etc. Looking to the right of the decimal point, that first decimal point, the tenths place, a tenth is 10 to the negative 1. A hundredth is 10 to the negative 2. A thousandth is 10 to the negative 3. And a 10,000th is 10 to the negative 4. In this class, and all mathematics classes, decimal representations of numbers are good, but we want to bring them back to other number systems, like the rationals. So we can rewrite this decimal as a rational number in the following way, and I'll cover rationals in a little bit. But just so you understand, 381.0259 is the same as this following. 3 times 10 squared plus 8 times 10 to the 1 plus 1 times 10 to the 0 plus 0 times 10 to the negative 1 plus 2 times 10 to the negative 2 plus 5 times 10 to the negative 3 plus 9 times 10 to the negative 4. So you can see you've got the numerals in each of the places times the power of 10 each place represents, and you add all those up. So that's how we can go from a decimal representation of a number to another representation of a number that's the same. This representation, this meaning of decimals informs the algorithms we use to add decimals and multiply decimals. So I'm going to take a second and just review that. So here I've got two decimals written to two decimal places, 47.58 and 28.61. Let's add them together. So when we add them, we line up the two decimals at the decimal point, and we add up in columns. So the 8 plus 1 gives us a 9. The 5 plus 6 gives us an 11. Well, we're going to take the 1 in the ones place and put that by the 9. And we're going to take the 1 that's in the tens place and move it to the top of the next column, because the next column is the next order of tens. Now we'll add up everything in this next column. 7 plus 8 is 15, plus that extra 1 is 16. So I'll put a 6 below the horizontal line, and I'll carry that 1 that's in the tens place over to the next column. And now I add 4 plus 2 is 6, plus 1 is 7. And there's our sum, 76.19. That's the sum. That's how we add two decimals. But you knew that. Let's look at multiplying two decimals. Here I've got the same two decimals. I'm going to multiply them. Here we're not so worried about lining things up, but we do want to keep track of how many decimal places we have. So one number is written to two decimal places. The other number is written to two decimal places. So we have a total of 4 decimal places that are accounted for. So let's keep that number 4 in mind. Now what we're going to do is that for each number, for each numeral, for each place in the second number, we're going to perform a multiplication, multiply that numeral by the number in the first row. So starting with the leftmost number, in this case 1, we're going to look at 1 times 47.58. Oop, wrong direction. We're going to look at 1 times 47.58. So that's the product. Easy peasy. Now we'll move over to the number in the tens place, with 6, and we'll multiply the first number, 47.58, times 6. So we'll do that starting from the ones place and moving left up to the tens place, or sorry, the hundredths place, moving up to the tens place. So 6 times 8 is 48. So I'm going to record the 8 in the second column and carry the 4. Then I get 6 times 5, which is 30. Add the 4, so 34. So I record the 4 and carry the 3, and so on. So this is what my paper might look like after I do that next product. Now I move to the third numeral in the second number, 8, and I'm going to do the same thing. 4758 times 8, and I get 38064. And then I move to the last numeral, the numeral in the tenths place of the second number, and do the multiplication. 2 times 4758, and I get 9516. Now, with these 4 numbers I have below, I want to add them together, and I just use the same algorithm that you just saw in the previous example. I add them together, 8, and then 8 plus 5 is 13, so I get a 3, carry the 1. 7 plus 4 is 15, so plus 1 is 16, 6 carry the 1, and so on and so forth. And then my last act is to remember how many decimal places we're working with. Since I started with 2 and 2 for a total of 4 decimal places, I put my decimal point 4 digits in. So that's how the algorithm for products work. You should be familiar with this algorithm. It's all based on that base 10 representation of decimal numbers. Why it works this way, we don't need to talk about. Just want to make sure that you all know it, make that connection with the decimal representation. There are other number systems. We'll start with the natural numbers. The natural numbers, also known as the counting numbers, are the set of numbers starting with 1 and then 2, 3, 4, 5, 6, and so on. If you include 0 in the set, you get a set that we call the whole numbers. So it's a different set from the natural numbers. A prime number is a number that is evenly divisible by 1 and by itself and nothing else. The smallest prime numbers are 2, 3, 5, 7, 11, 13, and 17. There is no largest prime number. Numbers that are not prime are called composite numbers. They are composed of prime factors, meaning they are the product of 2 or more prime numbers. Some of the smaller composite numbers are 4, which is 2 times 2, 6, which is 2 times 3, 12, which is 2 times 2 times 3, and so on. So there's a theorem called the fundamental theorem of arithmetic that says every natural number has a unique prime factorization. This means that each natural number can be written as a unique product of primes and powers of primes. Finding the prime factorization of a number can be a challenge, so I like to turn to software to help make sure I got it right. And here's a URL for the tool Wolfram Alpha that can help make that task easier. This fundamental theorem of arithmetic is really important to us as we do arithmetic and basic algebra, but it's important to note that polynomials have an analogous factorization property described by the fundamental theorem of algebra, and we'll see this in the next lesson. So the parallel here is important, and it's helpful for remembering how these things work. So if you understand what happens with composite numbers, that's going to help you understand what happens with polynomials. Another number system that's really important to us are the rationals. To understand what the set of rationals are, we're going to start with the set of integers. The set of integers is the set of positive and negative counting numbers, along with 0. So think of the natural numbers, put a copy of them in here. You see the 1, 2, 3, etc. Take their negatives. So here we've got negative 1, negative 2, negative 3. And then add 0. Like the reals, the set is closed under addition and multiplication. The set of rational numbers, which we denote by a q, is the set of numbers that can be written as a ratio of 2 integers. We describe this number system using set notation as follows. Q is the set of numbers of the form n over m, where n and m are both integers. Your experience should support the thought that the sum and product of 2 rationals is also rational. But let's work through this with an example so we make sure that we're all on the same page. So here's the number p, negative 7 over 13, that's a rational number. And another number, q, 24 over 5, that's also a rational number. So let's look at their product. P times q, so here I wrote p times q, negative 7 over 13 times 24 over 5. And rewrote that using the rules for multiplying rational numbers. So when you multiply 2 rational numbers, you take their numerators and multiply them, and you divide them by the product of their denominators. So multiplying that out, we'll get some number on the order of 168 over 65. So negative 168 over 65. When you multiply two rational numbers, you take their numerators and multiply them, and you divide the product of their denominators. Since the product of integers is an integer, the numerator and denominators are both integers, so the product of p and q is a quotient of integers, so it's a rational number. When you add two rational numbers, and here I'm using the same rationals, p and q, we know that you need to find a common denominator before you put the numbers together. So here the common denominator we're going to use is 13 times 5. So to change negative 17 over 13 to have a denominator of 13 times 5, we have to multiply the numerator and the denominator both by 5, which is fine. That's just a 1. To convert 24 over 5 to a number that has a denominator of 13 times 5, we need to multiply the numerator and the denominator by 13. So we multiply 24 over 5 by 13 over 13. Multiplying two rational numbers means you multiply their numerators and divide by the product of their denominators. Our denominator is 65. And so this means when we add, since they've got the same denominator, then we can just add the numerators. And in this case, we get a negative 277 over 65. Now, look at this number. The numerator and the denominator are both integers, so the sum of our two integers is a rational number. This demonstrates in this case that the product of two rational numbers is rational, and the sum of two rational numbers is also rational. Now, that was just a specific example. It doesn't prove it for all rational numbers. At the heart and soul of the academic area of mathematics are axioms, statements that we take to be true on face value, definitions, like the definition of the rational numbers, and theorems. Theorems are a mathematical statement shown to be true through a process of rigorous mathematical, logical proof. In this course, we don't focus on rigorous proof, but we help you appreciate this skill of proving things by showing you the mathematical way of looking at the world. We'll conclude this lesson with a simple proof of the following theorem. If p and q are rational numbers, then so are the numbers minus p, p times q, and p plus q. If p is not 0, then p to the negative 1 is rational too. And you'll remember that p to the negative 1 is the same thing as 1 over p. So what follows is a proof of this theorem. And I'll just read through it, and you can replay this as you try to wrap your head around it and understand each of the steps. So consider the case where both the numbers p and q are 0. Then negative p is negative 0, which is 0, and that's a rational number. P plus q is 0 plus 0, which is 0, is also rational. And p times q, which is 0 times 0, which is 0, is also rational. So all three of those numbers in the theorem statement I've just shown are rational numbers if both p and q are 0. Now, what if one of the numbers is 0 and the other is not? Say q is 0 and p is not 0. Then p plus q is p plus 0 is p, when p is a rational number, so p plus q is rational. P times q is p times 0, which is 0, is a rational number. And then, since p is not 0, there are integers n and m for which p equals n over m by the definition of a rational number. Then look at minus p. Minus p is minus n over m, which is the same thing as minus n over m. Since minus n is an integer, I've just shown that minus p is a ratio of integers, so minus p is a rational number. Also notice that p to the minus 1, if p can be written as n over n, p to the minus 1 is the quantity n over m to the minus 1. Well, a negative 1 exponent inverts ratios, so p to the minus 1 is m over n, but that's also a ratio of integers. Hence, p is rational. So this paragraph went through the arguments that prove the theorem in the case that one or both of the rational numbers are 0. All that remains to be shown is that the theorem is true when both rational numbers are non-zero. If both p and q are non-zero rational numbers, there are integers a, b, c, and d, for which p is a over b and q is c over d. Then p times q is a over b times c over d, which is the same thing as a times c over b times d. Since a times c and b times d are integers, p times q is a ratio of integers, so it's a rational number. Meanwhile, p plus q is a over b plus c over d. We need to find a common denominator. Our common denominator is going to be b times d. So a over b, we multiply it by d over d. C over d, we multiply by b over b. Using the definition of product of rationals, that's a times d over b times d, plus c times b over b times d. The denominators are the same by the commutativity of multiplication. So we can write this as one fraction, looking at the numerator as the sum of the two numerators. Since a times d and c times b are integers, so is their sum, so the numerator is an integer. B times d is an integer, so p plus q is now a ratio of two integers. This shows that p plus q is a rational number. This completes the proof of the theorem. Right? That's an example of a rigorous mathematical proof. Before drawing this lesson to a close, let's circle back to the idea that the concept of multiplication traces back to addition, and the concept of exponentiation traces back to multiplication. Exponentiation and exponents are important concepts in this course. When we work with exponents, we need to remember that we do so according to the law of exponents, which we summarize now. So for what follows, let a and b be real numbers, and let n and m be counting numbers. The following identities comprise the law of exponents and tell us how we can manipulate expressions involving exponents. So here I think there are 10 of them, and I'll let you pause the video and review them. You've had at least some practice using the law of exponents in the courses you've taken leading up to this course. So the professor expects that you are able to use these with some confidence. If you need more practice with these laws, or if you need practice with any other concept in this review material, approach your professor and talk about it. They'll help you find ways to practice and gain more confidence in these essential materials. In closing, through this lesson, we have reviewed the following concepts: the ways we use symbols in mathematics to represent quantities and processes, what a real number is and some properties of real numbers, how we work with numbers in decimal form, the natural, whole, integer, and rational number systems, prime and composite numbers, and the law of exponents. And the lesson has shared a mathematical proof about the rational number systems. Thank you, and I look forward to presenting Review 2 next.